about extreme values. And so now let's take a look at some of the theorems that are associated with extreme values. And for this video, we're going to focus on Rolle's theorem. In my next video, I'll focus on mean value theorem, which is kind of a more broad and generalized formula or theorem for Rolle's theorem. Rolle's theorem is very, very specific. So let's take a look here. We're being asked to plot these points for the function and then connect them. So let's just take a minute. We'll plot each of the values here. Let's see, 4 and 8. And then 6 and 10. 8 and 11. And we're coming back down, 12 and 8. And then 14 and 5. Pretty nice parabola looking motion here, isn't it? And so we're asked to connect those. Okay, so remember that the derivative has many, many applications, okay? One of them that is the most important is that the derivative represents the rate of change of a function. So when we look at rates of change of a function, we can talk about the average rate of change on an interval versus the instantaneous rate of change. So if we're looking for the average rate of change for this particular function, for any particular function, then we would look for the slope of a secant line. A slope of a secant line. That would be when we take 2 points that are on a curve and get my handy dandy Sonic gift card here. I'm going to have to use that gift card someday. Remember that the secant line is a line that runs through 2 points on the graph. So if we're looking for the average rate of change, we want the slope of the secant line. Friends, we're going to do this by this formula. And I hope that looks very, very familiar. May not look familiar in this form, but possibly like this, you've seen it. Right? It's slope, right? It's algebra 1 slope. But when we do it with a secant line on an interval from A to B, then our slope really looks like this, right? It's the y value at B minus the y value at A over B minus A. Same, same. Okay. When we're looking for the instantaneous rate of change, this is where we're doing the slope of the tangent line. If we're looking for the slope of the tangent line at x equals a, then that would just equal f prime of a. So let's see if we can take a look at it, right? Find the average rate of change from 2 to 12. So 2 to 12. We want the slope of this secant line. Okay, so my point at 2 is 2, 5, and my point at 12 is 12, 8. So if I want the average rate of change, I'm going to do the slope between these two. The rate of change. So I would do 8 minus 5 over 12 minus 2. Right? Just is calling it the average rate of change. So I get on top 3 minus 10. Now remember, if you did it the other way, if you did 5 minus 8, 2 minus 12, you would still get the same value. You remember that from your algebra days. Okay. Now, when we're looking at the instantaneous rate of change, remember that slope of the tangent line. This question asks us, is the instantaneous rate of change at x equals 4, which is here? Let me draw that little tangent line. Is the instantaneous rate of change at x equals 4 greater than the instantaneous rate of change at 6? So look at those little tangent lines. Now, granted, I haven't drawn them perfectly, but you can clearly see that the one at 4 is a little steeper than the one at 6. So the instantaneous rate of change at 4 has to be greater. Yes, because the slope of the tangent line at x equals 4 is steeper than the slope of the tangent at x equals 6. So we're the thing that is important is that you're able to go interchangeably between instantaneous rate of change, slope of tangent, derivative. All three of those mean the same thing. So if you're given one, you can find the other two. If you're given a different one, you, like I said, find the other two here. Okay, so let's look at what Rolle's theorem actually tells us. Rolle's theorem tells us that if the function is continuous, man, it seems like everything hinges upon the function being continuous, doesn't it? On a closed interval from a to b, it's differentiable on a to b. So that means no holes, no jumps, no discontinuities, no cusps, no sharp turns. And one more condition, and f of a equals f of b. Remember, those are our y values. So we're saying the endpoints have to be the same y value. Then there is guaranteed to exist a value of c on a to b where f prime of c equals 0. Now, like I said, this video is mainly about Rolle's theorem. The next video about mean value theorem is going to do a little bit more broader approach. So you've got a lot of conditions, right? Got to be continuous, got to be differentiable, and those y values have to be equal on the endpoints. So consider that function that we were just talking about, and let's look and see if Rolle's theorem would apply on these intervals. So I'm going to bring my graph back so we can see it. I've got my intervals here. So from 2 to 14, does Rolle's theorem apply? Is it continuous? Yes. Is it differentiable? Yes. Do the y values equal? So no, they do not. So Rolle's theorem doesn't apply because f of 2 does not equal f of 14. Oh, you know what? Did I do that? Let's see. F of 2, actually it does. Look, I went to 16 when actually it should be 2 to 14. So Rolle's theorem, let's just fix that, applies because f of 2 equals f of 14. F of x is continuous and it's differentiable. Now you can see where I'm going with the next one, right? So looking at 2 and 8, so 2 and 8 is here. It's continuous, it's differentiable, but those y values are not equal. That is why Rolle's theorem doesn't apply. Because f of 2 does not equal f of 8. Okay, now that we understand what Rolle's theorem is telling us, let's apply it. Okay, so each of these functions determine if Rolle's theorem is applicable Then apply the theorem to find the value that is guaranteed. Okay, so let's see, is it continuous? Yeah, no problems there with domain. Differentiable? Yep, I don't see any corners, cusps problems. Let's find out if those y values are the same. So g of -3 would be 9 times -3 squared minus -3 to the fourth. So it's 9 times 9 is 81 minus 81. That gives me 0. And g of 0 equals, looks like we're going to get those same y values. Good. Okay, so now we know that there's a place where the derivative equals 0. So let's take that derivative, set it equal to 0. I'm going to go ahead and factor out a 2. Oops, I should take a 2x, shouldn't I? 9 minus 2x squared. So I've got where x equals 0, or I've got 9 minus 2x squared equals 0. Now, x equals 0 is not on the closed interval -3 to 0. So I've got to have one from here. I'll move the 9, divide by 2, and I've got that x equals 3 over the square root of 2, plus or minus. So x equals plus or minus 3 square root of 2 over 2. But remember, we're only guaranteeing the one on this interval, which of course would be the negative one here. And that's what's guaranteed, that there's a place where the derivative equals 0 on this interval, and it happens right here at this value. Okay, look at number 2 then. Does Rolle's theorem apply? Is it continuous on this interval? Ah, I got a problem right there, don't I? So we've got that Rolle's theorem doesn't apply because g of x is not continuous at x equals -2. So I hope that helps with Rolle's theorem. I will go ahead and put the link to the next video, which would be mean value theorem. So you can kind of get the big picture of all of the theorems together. But thanks so much for watching.